We begin this lecture by discussing equivalence relations. If you are well familiar with this concept, so please fast forward to the place where we return to the context of linear algebra. Definition. Let A be a set. A relation R on the set A is a function from the set of pairs of elements of A to the set true-false. Notations. For elements x and y in the set A, we write x is related to y whenever R of xy is true. Let's give a couple of examples. Take A to be the set of real numbers and consider the relation x is less than y. If we write this relation as R of xy, then we will get that R of 3, 7 is true and R of 2, 1 is false. As another example, we can take as our set the set of integers and consider a relation x is equal to y mod 7. In this example, R of 5 and negative 2 is going to be true, and R of 1, 3 is going to be false. Let us give several definitions. A relation R on a set A is called reflexive if for every x in the set A, x is related to itself. Let's give some examples. If we take as our relation to be less on the set of real numbers, then this relation is not reflexive. So here we see that, for example, 5 is less than 5, so this is false. However, if as our relation we take less or equal to on the same set of real numbers, then this becomes reflexive. Because we know that for all x in real numbers, we can write that x is less or equal to x. So this will be true. And 3, if we consider the relation x is equal to y mod 7 on the set of integers, then it is reflexive. Since for all x in Z, x is equal to itself mod 7. Let us consider the following relation. R on the set of real numbers, where R of xy is defined as x times y is greater than 0. Here we will have, for example, that R of minus 2 is true, but R of 0, 0 is going to be false, since we put the strict sign here. And so the conclusion that this relation is not reflexive, because this property must hold for all x in our set. If we modify this example and take as relation R to be x times y is greater or equal to 0, then this relation becomes reflexive. Because it's true that for all x in real numbers, x times x is greater or equal to 0. Let us give two more definitions. A relation R is called symmetric if for all x in A and for all y in A, if x is related to y, then this implies that y is related to x. And a relation R is called transitive if for all x, y, and z in the set A, if x is related to y and y is related to z, then these two imply that x is related to z. Now let us investigate whether these relations possess the properties of being symmetric and transitive. So let's start with relation less. Well, this relation is not symmetric. So we have 3 is less than 5, but 5 is not less than 3. And the same applies for less or equal to. So this is not symmetric. The relation x equals y mod 7 is symmetric, because if x has the same remainder as y mod 7, then y has the same remainder as x mod 7. So this is symmetric. Now, this relation here, so x times y is greater than 0. So clearly this is symmetric, because if x times y is greater than 0, then y times x is still greater than 0. So this relation is symmetric. And the same applies to relations x times y is greater or equal to 0. This one is symmetric as well. Now let us look at transitivity of relation less. So here we have that for all x, y, and z in real numbers, we know that if x is less than y and y is less than z, this implies that x is less than z. So this tells us that this relation is transitive. And the same applies to the relation less or equal to. Exactly the same argument holds. So this one is transitive as well. The relation x equals y mod 7 is also transitive, because this says that y minus x is divisible by 7. And so if we know that y minus x is divisible by 7 and z minus y is divisible by 7, then z minus x will be divisible by 7. So this means that this relation is transitive. The relation x times y is greater than 0 effectively says that either both x and y are strictly positive, or both of them are strictly negative. So we get that if x and y have the same sign, and y and z have the same sign, then x and z will also have the same sign. So this relation is transitive. The relation x times y is greater or equal to 0 is not transitive. So here we have the following example. So we have r of 3, 0. This is true. Then r of 0 minus 5 is also true. So these products, 3 times 0 is greater or equal to 0, and 0 times negative 5 is greater or equal to 0. But r of 3, negative 5 is false. So this tells us that this relation is not transitive. So far, we were laying groundwork for the following definition. A relation R on a set A is called an equivalence relation if it is reflexive, symmetric, and transitive. So what we see is that among this list of relations, only this equality mod 7 is an equivalence relation. And other relations are not. Let us give examples of equivalence relations. Well, our first example is x is equal to y mod 7. Well, clearly we can replace 7 with any other base and get another equivalence relation on the set of integers. For our second example, we take A to be the set of triangles on a plane, and the relation is that so T1 is related to T2 if T1 and T2 are congruent triangles. As our third example, we can take the same set of triangles on the plane, and we can say that T1 is equivalent to T2 if T1 and T2 are similar triangles. Let us check that congruency of triangles is an equivalence relation. We know that any triangle is congruent to itself, so thus this relation is reflexive. Then if T1 is congruent to T2, then T2 is congruent to T1. So hence this relation is symmetric. And if T1 is congruent to T2 and T2 is congruent to T3, then triangles T1 and T3 are also congruent. So this gives transitivity. And because all these three properties holds, this relation is reflexive, symmetric, and transitive, this is an equivalence relation. The same argument works for similarity of triangles. For our next example, let's take A to be the set of vectors AB on the Euclidean plane. So here, each vector is determined by its starting point and the end point. So if E is the set of points on Euclidean plane, then our set A is really the set of pairs of points. So this cross here is a notation for Cartesian product. Which is the set of pairs. So here we say that elements of this set are ordered pairs of points. And the first point, A, is the starting point of a vector, and the second point, B, is interpreted as the end point of a vector. As a relation, we take equality of vectors. Let us show that this is an equivalence relation. So it is reflexive because for all pairs of points AB, we know that the vector AB is equal to itself. The symmetric property says that for all pairs AB and CD, if AB is equal to CD, then this implies that CD is equal to AB. Keep in mind that elements of the set A in this example are not points on the Euclidean plane, but rather pairs of points, that is, vectors. And we have transitivity, so which says that for all AB, CD, and FG, if we have that AB is equal to CD and CD is equal to the vector FG, then the vector AB is equal to the vector FG. Since these three properties hold, equality of vectors is an equivalence relation. Let tilde be an equivalence relation on a set A, and let X be an element of A. Definition: an equivalence class of X is the following subset in A. So it's denoted as class of X. So this is the set of all Y in A to which X is equivalent. Now let us give some examples. So suppose our relation is X is equal to Y mod 7. Then what's an equivalence class of 12? These will be all integers that have the same remainder after division mod 7 as 12. So that is 5. And we'll have 12 in this class, 5 is in this class. And if we add multiples of 7 to 12, then we will get elements that are equivalent to 12 under this relation. So this means that we will have 19 is equivalent to 12, 26, then 33, 40, and also we can go backwards. So negative 2 is equivalent to 12, negative 9, and so on. So we see that the equivalence class is an infinite set in this case. If we take an equivalence class of 5, then this will be actually the same set. And an equivalence class of 0 will consist of all multiples of 7. So it will be 0, 7, 14, 21, and in the negative direction, minus 7, minus 14, and so on. So if we take a relation of congruency of triangles, then an equivalence class of T is the set of all triangles congruent to T. And for the relation which is equality of vectors, so the class of a vector AB is the set of all vectors CD such that CD is equal to AB. Now let us state our main theorem about equivalence relations. Theorem: let tilde be an equivalence relation on a set A. Then 1. A is a union of equivalence classes. And two equivalence classes either do not intersect or coincide. So here, if we take the set A and draw equivalence classes, then we are saying that A is covered by the equivalence classes, and these equivalence classes do not overlap, or if they overlap, then they completely are equal. So the claim of this theorem may be stated in other words is that A is a disjoint union of its equivalence classes. So we can write A as a union of equivalence classes that do not overlap. Now let us look at our example of the relation when x is equal to y mod 7. Here we have a class of 0, which is the set of all multiples of 7, so 0, 7, 14, and minus 7, and so on. Then we have a class of 1, which is 1, 8, 15, so these are all integers that have remainder 1 after division by 7. So we have a class of 2, so this will be 2, 9, 16, and minus 5. Then we have a class of 3, so which will contain elements 3, 10, 17, and minus 4. Then we have class of 4. So these are all that have remainder 4 after division by 7. We have a class of 5, so which will have 5, 12, 19, minus 2. And we have a class of 6, which will have 6, 13, 20, and minus 1. And if we try to take a class of 7, then we will see that this class will be the class of all multiples of 7. So this means that the class of 7 is completely equal to the class of 0. And the class of 8 is completely equal to the class of 1. And the class of minus 1 is exactly the same as the class of 6. So we see that some equivalence classes have empty intersection, and some equivalence classes are completely equal. So this is what the second part of this theorem states, that two classes either do not overlap or completely coincide. Now, the first part of this theorem says that the set Z is the union of equivalence classes. So if we take equivalence class of 0, equivalence class of 1, 2, 3, 4, 5, and 6, then these 7 equivalence classes together completely cover the set of integers. So this is what we're saying here, so that the set of integers is a disjoint union of these 7 equivalence classes. So what we see here is that equivalence classes in this example correspond to remainders mod 7. So for example, the class of 2 is the set of all integers with remainder 2 mod 7. And this gives us a new take on the set Z7. So we can think that Z7 is the set of these equivalence classes. So it's equivalence class of 0, equivalence class of 1, up to equivalence class of 6. Now let us give the proof of this theorem. So for 1, we say that this relation is reflexive. So this tells us that for every x in A, x is equivalent to x. But then this implies that x belongs to its own equivalence class, because the equivalence class of x is the set of all y that are equivalent to x. But since x is equivalent to x, we get that x is in this equivalence class. And this tells us that every element of A is in some equivalence class. Hence, the union of equivalence classes is the set A. Now let us prove part 2. Suppose equivalence class of x and equivalence class of y overlap. That is, there exists an element z such that z belongs to both the equivalence class of x and it belongs to equivalence class of y. We need to show, in this case, that these two classes are completely equal. And how do we show equality of two sets? So we need to show that equivalence class of x is inside equivalence class of y, and that equivalence class of y is inside equivalence class of x. Let us show that equivalence class of x sits inside equivalence class of y. Let w be an arbitrary element in equivalence class of x. So we need to show that w is an equivalence class of y. So what do we have? So we know that w belongs to equivalence class of x. So this means that x is equivalent to w. We also know that z belongs to equivalence class of x. So this tells us that x is equivalent to z. And finally, we know that z belongs to equivalence class of y. So that is y is equivalent to z. And what we need to show is that w is an equivalence class of y, so that is y is equivalent to w. By symmetry, since we know that x is equivalent to z, so this also tells us that z is equivalent to x. Now we have that z is equivalent to x, and x is equivalent to w. And then by transitivity, we have that z is equivalent to w. So now, finally, we have that y is equivalent to z, and z is equivalent to w. And again, applying transitivity, we get that y is equivalent to w. But that's exactly what we had to show. Since y is equivalent to w, we conclude that w belongs to equivalent class of y, and w was an arbitrary element in the equivalence class of x. So this tells us that the equivalence class of x is completely inside the equivalence class of y. But this proof is symmetric, so we can now just switch x and y, and this will give us that equivalence class of y will be inside equivalence class of x. And what we did is we assumed that equivalence class of x and y have a common element, and we proved that these two classes are completely equal. This tells us that we have just two possibilities. Two equivalence classes may be either completely equal or completely disjoint. Direct sum construction allows us to build bigger vector spaces from smaller ones. This is an analog of addition operation on the set of natural numbers. The quotient space construction, which we are going to discuss next, is an analog of subtraction in this context. Let V be a vector space over a field F, and let U be a subspace in V. So we introduce the following relation on our vector space, where we say that vector V is related to vector W if and only if the difference of V and W belongs to the subspace U. So we have the following proposition. This relation on the space V is an equivalence relation. So to prove that something is an equivalence relation, we need to establish that it satisfies all the three properties. So that is, this relation is 1, reflexive, 2, symmetric, and 3, transitive. So let us start with the first property. So what does reflexive means? So this means that every vector in V is related to itself. But what does it mean? So now we use our construction of this relation. So this is equivalent to saying that for every V in V, V minus V belongs to the subspace U. And this is equivalent to saying that 0 vector, so because V minus V is equal to 0 vector, is in U. But this holds since U is a subspace. And we know that every subspace contains a 0 vector. Now let us look at the second property of that this relation is symmetric. This means that for all vectors V and W in our vector space, if V is related to W, then this implies that W is related to V. Now let us spell out our relation. So equivalently, we are saying here that if V minus W belongs to the subspace U, then we need to show that W minus V also belongs to U. But what is W minus V? So W minus V is equal to minus 1 times V minus W. And here, by our assumption, V minus W belongs to U. And U is a subspace. So if we take any vector in U and multiply it by a scalar, in particular by scalar minus 1, the result is still in U. So this is in U, since U is a subspace. And finally, we need to prove that this relation is transitive, which means that for all V, W, and S in the space V, if V is related to W and W is related to S, then this implies that V is related to S. Now, let us spell this out using our construction of this relation. So equivalently, this can be written in the following way. So if V minus W is in subspace U and W minus S is in the subspace U, we need to check that V minus S is also in the subspace U. But here we have that V minus S can be written as a sum of V minus W and W minus S. And here we know that the first summand belongs to the subspace U, and the second summand belongs to the subspace U. And U is a subspace. So if we take two vectors in U and add them, the resulting vector is also in U. So we conclude that this is in U, since a subspace is closed under addition of vectors. So if we have two vectors in a subspace, then their sum is again in the subspace, and this shows transitivity of this relation. So we proved that this relation is reflexive, symmetric, and transitive, so it is an equivalence relation. Whenever we have an equivalence relation, we know that we can represent our set as a disjoint union of equivalence classes. So this tells us that our vector space V now is a disjoint union of equivalence classes. So let us look at equivalence classes. So what's an equivalence class of a vector V? So this is the set of all vectors W in V such that V is equivalent to W. Or, so if we spell out our equivalence relation, so this is the set of W in the vector space V such that V minus W is in U. And because our relation is symmetric, so this can also be written as the set of all W's in V such that W minus V is in U. We will use these two properties interchangingly. In particular, it's interesting to point out what's an equivalence class of a zero vector. So by our last definition, it's the set of all vectors in the vector space V such that W minus 0 belongs to U. But this says that W actually belongs to U, right? So this is the set of vectors in V that belong to U. Well, this is exactly the set U. And we see that the equivalence class of a zero vector under this equivalence relation is our subspace U. Another way of writing these equivalence classes is the following. So we can say that the equivalence class of V is equal to the sum of V plus the subspace U. Now, what do we mean by this notation? So here we take one vector and add to it a set. So this, by definition, stands for the following. So we take sums of V plus vectors U, where vector U runs over this subspace U. This is the meaning of this sum. Now let us show that this is equivalent to what we had before. So before we said that our equivalence class is the set of all W's in V such that W minus V belongs to U. But we can write W as V plus W minus V. So this becomes the set of V plus W minus V, where W minus V belongs to U. And finally, so let us set vector U be W minus V. And then this set becomes V plus u, where u runs over the subspace u. And that's exactly what we claimed here. For this set v plus u, so we will sometimes use terminology that this is coset of u. Now let us look at some examples. Let's take v to be R2 and u be the span of vector 1, 0. So that is x-axis. Here our vector space is a plane and our subspace is this horizontal line. Now what will be the coset of a vector v? So here what we do is we consider sums. So we take vector v and we add all possible vectors from the subspace. So this means that we add all possible horizontal vectors to it. And the resulting equivalence class of this vector will be this horizontal line. So this horizontal line will be v plus u, or this is an equivalence class of a vector v. What will be other equivalence classes? So the equivalence classes in this picture are horizontal lines. And then we see this theorem that says that our set is a disjoint union of equivalence classes. So here we see that this plane is covered as a disjoint union of these parallel horizontal lines. We could have two vectors that have the same equivalence class. So we see that two equivalence classes either completely coincide or do not overlap. And the set of all equivalence classes covers our vector space. For the second example, let's take v to be R3 and u be the horizontal plane. So that is the span of vectors 1, 0, 0 and 0, 1, 0. Here our subspace is the horizontal plane, and to construct an equivalence class of a vector, we take this fixed vector v and add to it various vectors that belong to this horizontal plane u. And so the resulting equivalence class will become a plane which is parallel to u and passes through the vector v. So this plane will be the equivalence class of v, which is v plus the subspace u. And then we see that the whole three-dimensional space can be decomposed as a disjoint union of these parallel planes. So these parallel planes will be various equivalence classes under this equivalence relation. And for our third example, so let's take v to be R3 and u to be one-dimensional space, say span of 1, 0, 0. So in this case, so u is this horizontal line, and then all equivalence classes with respect to this equivalence relation induced by this subspace. So we will get all lines in three-dimensional space that are parallel to the line u. This will be the description of cosets or equivalence classes in this case. Now we formulate our main definition, which is at the same time a theorem. So here we define the quotient space. And the notation for this is v quotient by u is the set of equivalence classes v quotient by u is the set of all equivalence classes under the equivalence relation induced by subspace u. And the theorem part of this definition is that this quotient space, v quotient by u, is a vector space over a field F with zero vector being the equivalence class of 0, so that is the subspace U. And the operation of addition of equivalence classes. So if we have equivalence class of V and we add an equivalence class of W, then by definition we get equivalence class of V plus W. So this is the operation of addition in this vector space, and we also have the operation of multiplication by scalars. So C times V by definition is the equivalence class of C times vector V, where C is a constant from F and V and W are in vector space V. Let us give the proof of this theorem. So here we need to prove that this quotient space is a vector space over a field F. So we need to show that the quotient space satisfies the axioms of a vector space. Well, it turns out that this task is secondary and it's quite easy. But the primary and more substantial task is to show that operations in this set, right? So we define these operations of addition and multiplications by scalars. So we need to show that these operations are well defined. This issue will always come up when we define operations on equivalence classes, because here we define these operations using the representatives. So here V and W's are representatives of an equivalence class. Our definition of addition of equivalence classes is the following. We choose representatives V and W in each of these classes, then we add them, and we take the equivalence class of the result. But there is more than one way of choosing a representative in an equivalence class, and we need to show that the resulting equivalence class is independent of the choice of these representatives. So this means the following, that if we have two vectors v1, v2, such that the equivalence classes are the same, and if we have two vectors w1 and w2 also with equal equivalence classes, then we need to show that equivalence class of v1 plus w1 is the same as the equivalence class of v2 plus w2. This would mean that addition given by this rule is well defined. So that is, it does not depend on the choice of the representative in our equivalence class. And we need to show that the operation of scalar multiplication is also well defined. So for this, we need to show that if v1 and v2 have the same equivalence classes, then we need to establish that C times v1 have the same equivalence class as C times v2. This would mean that the operation of multiplications by scalars is well defined. So let us prove that addition is well defined in the quotient space. So here we assume that the equivalence classes of v1 and v2 are the same, and the equivalence classes of w1 and w2 are the same. And we need to show that the equivalence class of v1 plus w1 is the same as equivalence class of v2 plus w2. Now, what does it mean that equivalence classes of v1 and v2 are the same? This means that v2 belongs to equivalence class of v1. And if we say this, we will conclude that these two equivalence classes overlap, and thus they coincide. So saying that these two equivalence classes are equal is the same as saying that v2 belongs to equivalence class of v1, And this is equivalent to saying that the difference of V1 minus V2 is in the subspace U. So likewise, if we say that equivalence classes of W1 and W2 are the same, so this is equivalent to saying that the difference between W1 and W2 is in the subspace U. And what we need to show is that the difference between V1 plus W1 minus V2 plus W2 is also in U, because this says that these two equivalence classes are equal. But now let us look at the left-hand side here. We have V1 plus W1 minus V2 plus W2. This equals to V1 minus V2 plus W1 minus W2. But we assumed that V1 minus V2 is in U, and W1 minus W2 is also in U, and U is a subspace, and so the sum of two vectors in the subspace belongs to the subspace. And here this proves exactly what we needed to prove. And the second part, so where we need to prove that multiplication by scalars is well defined. So this I leave for you as an exercise. Now that we proved that operations in the quotient space are well defined, verifications of axioms is very easy. So let us look at one particular example. So let us look at distributive law. One of the distributive laws says that C times V plus W is equal to C times V plus C times W. Now let us look at the left-hand side. So what is the left-hand side? So C times V plus W. So here, the way how we defined addition of equivalence classes is it's an equivalence class of the sum. So this becomes C times the equivalence class of V plus W. And the way how we defined multiplication by scalars, so this is an equivalence class of C times V plus W. Now let us look at the right-hand side. In the right-hand side, we have C times equivalence class of V plus C times equivalence class of W. So this is the class of C times V plus the class of C times W. And the sum of these two classes is equal to the class of C times V plus C times W. But we know that V satisfies the axioms of a vector space. So the distributive law holds in V. So we know that in V we have this equality, that C times V plus W is equal to C times V plus C times W. This is one of the axioms of a vector space. And from here, so since these two vectors are the same, then these two equivalence classes are also the same. So we get that the right-hand side is equal to the left-hand side. And this proves that the distributive law holds in the quotient space, and verification of all other axioms is just as straightforward. And so I leave this for you as an exercise. This proves that the quotient space is indeed a vector space. It is instructive to revisit remainders and to see that what we did here for quotient space is very similar to what we have done for remainders. So we can define remainders using an equivalence relation, where we say that two integers are equivalent if their difference is divisible by m, where m is the modulus. And when we defined addition and multiplication of remainders, we said the following. So let us take an equivalence class. So that is a remainder modulo m. And here is how we defined addition and multiplication of remainders. we said, take two equivalence classes and pick representatives in these equivalence classes. So that is integers with the corresponding remainders. And we define addition of equivalence classes as the equivalence class of the sum of the two representatives. And the difficulty that we faced there was exactly the same as we had here. So we had to prove that this operation is well defined. So that is, addition of remainders is independent of the choice of representatives in these equivalence classes. And we did the same for multiplication. So we see that the construction of the quotient space follows exactly the same pattern as the construction of remainders. These parallels between the two constructions will be systematically explored in the second-year course on algebra. Now let us discuss the canonical projection. Here we have a proposition. There exists a linear transformation P from the space V to the quotient space V quotient by U, which is called the canonical projection, defined by P of a vector V is equal to the equivalence class of this vector. So here, to each vector, we associate its equivalence class. And this will be a transformation from vector space V to vector space V quotient by U. We need to prove that P is linear. So this means two properties. That one, P of V1 plus V2 is equal to P of V1 plus P of V2. And the second property, that P applied to constant times V is equal to constant times P applied to V. Now, let us apply the definition of our linear transformation P. So 1 becomes equivalent to the following. So that we say that the equivalence class of V1 plus V2 is equal to equivalence class of V1 plus equivalence class of V2. And the second property now reads that equivalence class of constant times V is equal to constant times equivalence class of V. But these are just definitions of our operations. So this is how we add equivalence classes and multiply them by scalars. And automatically, these two properties hold. So this tells us that this canonical projection P, where we associate to each vector its equivalence class, is in fact a linear transformation. We see the following properties of canonical projection. First of all, the canonical projection is surjective. This is obvious because an equivalence class of vector V as a preimage has vector V itself. And the second property, so let us look what is the kernel of the canonical projection. So the kernel of the canonical projection is the set of vectors V such that equivalence class of V is equal to 0 vector. But this 0 vector is a 0 vector in the quotient space. And the 0 vector in the quotient space is the subspace U. So what we see is that the kernel of canonical projection is the set of vectors that belong to the subspace U. So this is the subspace U. Now we get the following corollary. That dimension of the quotient space is equal to the difference of dimension of V minus dimension of U. And so what we see is that the quotient space is an analog of the subtraction operation. So how do we prove this? So to prove this, we apply rank nullity formula to the canonical projection P, which says that dimension of the kernel of P plus dimension of the image of P is equal to the dimension of the domain space V. Now, the kernel of P is a subspace U, so we get the dimension of U plus the image is, since P is surjective, so the image is the quotient space, V quotient by U. So we get dimension of the quotient space. And the sum of these two dimensions is equal to dimension of V. And from here, we immediately obtain the claim that dimension of the quotient space is the difference of dimension of the whole space and the subspace U that defines this quotient space. Now let us state the following theorem. Let U be a subspace in V, and let the set U1 through UK be a basis of U. And let W1 through WS be a set of vectors in V. Then our first claim that the set of equivalence classes W1 through WS spans the quotient space if and only if the set U1 through UK, W1 through WS spans V. Our second claim is that the set of equivalence classes W1 through WS is linearly independent in the quotient space if and only if the larger set U1 through UK, W1 through WS is linearly independent in V. And combining these two properties together, we get that the set of equivalence classes W1 through WS forms a basis of the quotient space if and only if the set U1 through UK, W1 through WS forms a basis of the space V. So essentially, this theorem tells us how to construct a basis of the quotient space. So for this, we need to take a basis in the subspace U and complete it to a basis of the space V. Then equivalence classes of the extra vectors that we added will form a basis of the quotient space V quotient by U. This construction also implies the dimension formula that we established, because here it says that the dimension of the space V is equal to the sum of the dimension of the quotient space, which is S, and the dimension of the subspace, which is K. So this says that dimension of V is equal to dimension of U plus dimension of V quotient by U. We begin with our first claim, and this is an if and only if statement, so this means that we need to prove two implications, going from left to right and from right to left. So we'll start with 1a. So here we assume that equivalence classes W1 through WS span the quotient space, and we need to prove that the set U1 through UK, W1 through WS spans V. So what does it mean? So this means the following, that we need to show that any vector in our vector space belongs to the span of these vectors. So let V be an arbitrary vector in V. So we need to show that V belongs to the span of this set of vectors, U1 through UK, W1 through WS. So how do we do this? So we consider an equivalence class of V as an element of the quotient space. So we know that equivalence classes W1 through WS span the quotient space. From here, it follows that there exist scalars C1 through CS in the field, such that equivalence class of V is equal to C1, the class of W1, plus CS, the class of WS. Now let us move everything to the left side. So this tells us that equivalence class of V minus C1 W1 minus CS WS is equal to the class of 0. And using the way how we define operations on our equivalence classes, so this tells us that the equivalence class of V minus C1 W1 minus CS WS is equal to equivalence class of 0, but this is our subspace U. And this tells us that the vector that we have here is in fact in this subspace. So this tells us that V minus C1 W1 minus CS WS belongs to U. But then here we know that vectors U1 through UK form a basis of U. So this tells us that there exist scalars D1 through DK in F, such that V minus C1 W1 minus CS WS is equal to D1 U1 plus DK UK. And this tells us that vector V is equal to D1 U1 plus DK UK plus C1 W1 plus CS WS. And this proves that our arbitrary vector V belongs to the span of this set of vectors, because we proved that it's a linear combination of this set of vectors. And this completes the proof of 1a. Now we need to prove the converse direction. So we have 1b. So we assume that the set U1, UK, W1, WS spans V, and we need to show that the set of equivalence classes W1 through WS spans the quotient space. Let the equivalence class of V be an arbitrary vector in the quotient space. Here, the vectors in the quotient space are equivalence classes. So here, vector V belongs to the vector space V. So this tells us, because we know that vector space V is spanned by this set of vectors, there exist scalars D1 through dk and C1 through Cs such that this vector V can be written as a linear combination D1 U1 plus dk UK plus C1 W1 plus CS WS. Let us take the equivalence class of both sides. So from here we get that the equivalence class of V is equal to the equivalence class of this linear combination D1 U1 plus dk UK plus C1 W1 plus CS WS. But we know that equivalence class of a sum is the sum of equivalence classes. So this can be written as D1 equivalence class of U1 plus dk equivalence class of UK plus C1 equivalence class of W1 plus CS times equivalence class of WS. But here we have that our vectors U belong to the subspace U. And because of this, the first k equivalence classes are just 0. So here we have D1 times equivalence class of 0 plus dk times equivalence class of 0 plus C1 equivalence class of W1 plus CS times equivalence class of WS. So here, this is based on the observation that if U belongs to the subspace U, this is equivalent to saying that equivalence class of U is equal to equivalence class of 0. And so the first k terms will vanish, and we will just get C1 equivalence class of W1 plus CK equivalence class of WK. And what we see is that equivalence class of V belongs to the span of equivalence classes of W1 through WS in the quotient space. And that's exactly what we had to prove here, that the set W1 through WS, the set of these equivalence classes, span the quotient space. Our second claim is that the set of equivalence classes of W1 through WS is linearly independent in the quotient space if and only if the combined set U1 through UK, W1 through WS is linearly independent in V. So let us prove the forward direction. So we assume that we have a linearly independent set in the quotient space, and we need to prove that the set U1 through UK, W1 through WS is linearly independent in V. And how do we prove linear independence? We consider a linear combination which is equal to a 0 vector, and we need to prove that all coefficients are equal to 0. So we consider D1 U1 plus dk UK plus C1 W1 plus CS WS, and we assume that this is equal to a zero vector. Let us take equivalence classes of both sides. So then we get that equivalence class of D1 U1 plus DK UK plus C1 W1 plus CS WS is equal to equivalence class of 0. And this tells us that D1 times equivalence class of U1 plus DK times equivalence class of UK plus C1 equivalence class of W1 plus CS times equivalence class of WS is equal to equivalence class of 0. But here, the first k vectors form a basis of U, and so this means that the equivalence classes are all 0. So from here we conclude that C1 times equivalence class of W1 plus CS times equivalence class of WS is equal to 0 equivalence class. By assumption, the set of equivalence classes W1 through WS is linearly independent in the quotient space. So this tells us that all these coefficients C1 through CS are equal to 0. But now we can go back to the larger linear combination where we have linear combinations of UIs and WJs. And because all the C coefficients are equal to 0, then from here it follows that the linear combination of U vectors, D1 U1 plus DK UK, must be equal to 0 vector in our vector space V, because all other terms will vanish because the coefficients C1 through CS are equal to 0. But we were given that the set U1 through UK is a basis of U. So we know that a basis is a linearly independent set. And from here we conclude that the coefficients D1 through DK are also must be equal to 0. And now we consider the linear combination of this combined set, which is equal to a 0 vector, and we proved that all D coefficients and all C coefficients must be equal to 0. And so this tells us that the combined set U1 through UK, W1 through WS is linearly independent in the vector space V. Now let us consider the backward direction. So this means that we assume that this set is linearly independent, and we need to prove that the set of equivalence classes W1 through WS is linearly independent in the quotient space. So for this, we consider a linear combination of these vectors which is equal to a 0 vector. Consider a linear combination C1 W1 plus CS WS, which is equal to a 0 vector, or equivalence class of 0. And we need to show that all these coefficients are equal to 0. So from here, we conclude that equivalence class of C1 W1 plus CS WS is equal to equivalence class of 0. When is the equivalence class of a vector is equal to 0 equivalence class? This happens precisely when this vector belongs to our subspace. So from here we conclude that C1 W1 plus CS WS belongs to the subspace U. But here we have a basis of our subspace. So this tells us that there exist scalars D1 through dk such that this vector C1 W1 plus CS WS is equal to D1 U1 plus dk UK. And then if we bring everything to one side, so we get that C1 W1 plus CS WS minus D1 U1 minus dk UK is equal to a zero vector. And this equality holds in V. But our assumption is that this combined set is linearly independent. And this implies that all coefficients in this linear combination are equal to 0. So this tells us that all C coefficients are equal to 0. And all D coefficients are equal to 0. But it's the C coefficients that we need. So we proved that the C coefficients are equal to 0. And here, what did we prove? So we considered a linear combination of equivalence classes of W1 through WS and equated it to a zero equivalence class. And we proved that all C coefficients are equal to 0. And this tells us that the set of equivalence classes W1 through WS is linearly independent in the quotient space. Combining properties 1 and 2, we immediately obtain property 3, that the set of equivalence classes W1 through WS is a basis of the quotient space, if and only if the combined set U1 through UK, W1 through WS is a basis of V. Now we can use this property to show the relationship between quotient spaces and direct sums. Let W be a subspace in V spanned by these vectors W1 through WS. So here we assume that this property 3 holds. By this property 3, we will have that the vector space V decomposes in the direct sum of subspaces U and W, because the basis of V is made up of a basis of U and the basis of W. So then we see that we have a one-to-one correspondence between the following spaces. The space V quotient by U will be isomorphic to the space W, because the basis of W is given by vectors W1 through WS, and the basis of the quotient space is given by the cosets of W1 through WS. And so we have a one-to-one correspondence here given by canonical projection. So we have a map P that sends a linear combination of basis vectors W1 through WS to the linear combination of the corresponding equivalence classes. And because each of the set is a basis in the corresponding space, we get that P is an isomorphism between the space W and the quotient space V quotient by U. And this shows us the relationship between addition of vector spaces and subtraction of vector spaces. We point out, however, that this subspace W is not determined by V and U. We have many ways how we can choose a subspace in V which is complementary to the given subspace U. So whereas the quotient space V quotient by U is determined just by V and U, the subspace W is not uniquely determined by these two spaces. And the choice of this complement is not canonical.